Now let us consider the test for two means, right? Test for difference of the two means. Okay, mu1 minus mu2. So null hypothesis is that mu1 minus mu2 is suppose 0 and the difference between the two is not equal to 0. So you have the two-tailed test. So again we have to import numpy as np. Okay, we need two sample data sets. So let me just mention, like group 1 would be np.array. So here you will write the observations. Suppose it is 23, 28, 32, 37, 44, 49, 55, 61, 70 and 78. Likewise we can get for another sample also. So let that be denoted by group 2, again an array. So np.array. So here we can change the values. So 30, 35, 42, 48. We can have 53 now, 59, 64, 72, 79 and 85. So here you have the procedure as you are generating. So you have the two samples. First of all, now you have to calculate their respective means, right? X bar and y bar. So for that, let us calculate the observed mean 1. So that will be np.mean, and for sample 1 we need, oh sorry, it is group 1 and observed mean 2 as np.mean group 2. Okay, so let me comment that. So these are your observed means. Observed means x bar and y bar. Once you have calculated these two, what do? We need to compute your observed test statistic also, right? So basically t is what? X bar minus y bar. Okay, so here we will compute your observed statistic. So let me write that as comment. Calculate t equal to x bar minus y bar. So let that be observed statistics. So I'm just using a short form here. So you will have observed mean 1 minus observed underscore mean 2. So you have calculated t now, right? Now you have to generate the bootstrap samples from these observed samples, and you will calculate for each sample, the sample mean would be calculated, and the process will be repeated for both of them. In the previous case, we were just working with a single sample. So we had the samples only from a given data set, one single data set. Now you have two of them, so you will generate from there. So we will write a function to generate a bootstrap sample and calculate your TI. So let us define a function. So we can give that a name as generate bootstrap, and here we would write the arguments as data 1 and data 2. Okay, so these will be the input. So we have to first of all draw the random samples with replacement. So we will mention that as sample 1 is equal to np.random.choice data 1. The size of that would be length data 1 replace is equal to true. Okay. So for the second sample also we will have the same thing. Again, we are going to draw a random sample with replacement from the second data set. The length obviously would be same as 2. Here we have considered them of the same size. Once you have taken the sample, you have to calculate their corresponding means. Okay, so sample mean 1 would be found using NumPy's mean function for the first sample, and sample mean 2, that is the second sample mean, np.mean for the sample 2. Okay, so now what it will return is the difference between these two. So sample mean 1 minus sample mean 2. Okay, so what have you obtained here? You have obtained x bar minus y bar, xi bar minus yi bar in fact. So for this is just for a single sample. So if I call this function again and again, suppose I iterate it for 1000 times, it means that we will get the difference of these two for 1000 number of times, right? So t1 to t1000. So now if I want to generate n bootstrap statistics, so I have not given the command for n. Let me just mention here as n as 1000. So generate n bootstrap statistics ti. So here bootstrap st I would use. This one would be, again I am going to call this function and it will be done iteratively for range n. Okay, so basically it means that I am going to iterate this loop for 1000 number of times. Okay, so basically here if you see I am using this underscore, this is just like a throwaway variable indicating that its value is intentionally not used. Okay, so it is common when you have to repeat an action a certain number of times, but you don't need the loop variable. So here if you define I don't need I again. So I can just keep it as underscore only. So once you have written this, what you obtain here, so this will give you a list of different TIs from T1 to T1000. Okay, and now we can compute your p-value. So p-value here would be np.mean, and you will compare the absolute value of the absolute value of your bootstrap statistics, bootstrap underscore st, if that is greater than equal to the absolute value of the observed statistic, right? Observed st. So here actually I should write not data 1, it should be group 1, because I am storing it in group 1 and group 2. Okay, so this one would be again bootstrap, absolute value of the bootstrap. So that is bootstrap here is ti, so mod of ti's, is it greater than equal to mod of t? So if it is, then it is going to be added to your I, otherwise it won't be considered, right? So if alpha is suppose 0.05, and now if you want to test whether the p-value is less than equal to alpha, then you print reject h0. Else what are you going to print? That is, we failed to reject. Print fail to reject h0, and now we can print the observed difference that we have obtained, observed difference in means. So print observed difference in means, that is t that we have obtained. So it will be observed underscore st. Sorry, it won't be a is equal to sign, but colon over here. And you also want to print, suppose, the p value. Again, I have made some mistake somewhere. Bootstrap. Bootstrap. Sorry. You have to be very careful with the spellings. If you write in a hurry, it will give you various errors. So you are going to reject the null hypothesis. Observed mean difference is -9. And the p-value obviously is much greater than alpha. So you fail to reject the null hypothesis. It means that the two population means, that is mu1 minus mu2, that is 0. That the two population means are same. You can conclude that. You do not have sufficient evidence to say that the two means are different. Obviously, if you change the values over here, you can get the different answer. It all depends upon whatever data set that you are given to utilize. The steps will be these. Okay, so you can see that how to generate a bootstrap sample. If you are given two samples or the two sample problem for hypothesis testing, you have to test for the difference of the two means. How you can compute all those things. You can find the p-value and everything else based upon your bootstrap concept. So we have done it for test for two means. Likewise, one can do for two population variances also, right? If you want to test the equality of two population variances. So let me write the test for population variances. So again, here also we have to import NumPy as NP. Now you need the sample data sets for the two populations. So let us use this only, group 1 and group 2. Maybe we can just rename it population 1 or population 2. 23, 28, these are 78, and here we can take it. Okay, fine. So these are the two samples. So you have xi's and yi's. Now you need the observed sample variances. So you need S1 square and you need S2 square. So these are the two samples that we have, or the two data sets that we have considered. Now what we have to do is you have to find out the observed sample variances. So what will be the first one? We can use this hashtag. You have to find out. The comment will be observed sample variances. And here the observed variance 1 can be found out using np.var, and we can write for population 1 with, that is, it means that we are specifying it will be the sample variance. And likewise you can also obtain for the second one, that is, so here we will write pop2 DDOF S1. So sample variances would be calculated. So you have S1 square and S2 square. Okay, now suppose you want to test whether sigma 1 square over sigma 2 square is 1, right? Basically means that you want to test whether the two variances are equal. You can also go for the difference of the two variances, or you can look at the ratio, but looking at the ratio makes more sense, right? Because interpretation in terms of the difference of variance won't make much sense. So we stick to, so here I am just going to show you how you proceed if you have to check the hypothesis testing for the ratio of the two sample variances. So in this case, your test statistic would be compute the observed test statistic, observed statistic, that is T, right? So T would be basically S1 square So maybe here notation might be a problem. So S1 square over S2 square. So what will you write? Observed statistic is observed variance 1. So ratio of these two, observed variance 2. So this is P that you have obtained. Now you can also specify the number of bootstrap samples that you want. It is 1000, and we can write the function to generate a bootstrap sample. So for that we will write define bootstrap sample. We can give the arguments as data 1, data 2, and here it is going to consider for the first sample. How will it be drawn? It will be done with replacement from the first population, from the first data set, and the size of that data set would be same as the length of the current data, population 1, and you will say replace is equal to true. Likewise you can write for the other one also. So sample 2 would be, so here we will just mention 2, and right, so random samples will be taken from this. Now for each sample we have to compute the sample variance. So sample variance 1 would be np.var, numpy is function. So sample, yes, sample 1, and we are specifying that we need the sample variance only, not the population variance. So sample variance 2 would be np.var sample 2 ddf as 2. So you have computed your sample variances, that is Si1 square and Si2 square. So it is going to return you the ratio of these two, right? So sample var 1 divided by sample variance 2. Now let us generate n bootstrap. Statistics, that is TIs. What will we do here? We will mention this bootstrap st. So here we will write this, we will call this function, that is generate. Sorry, it will not be generate, because the name of the function here is bootstrap underscore sample. Here we are going to write population 1 and population 2 for in range. So we are going to initiate a for loop 1000 number of times, right, for each bootstrap sample. Okay, so 2 samples will be drawn from these 2 data sets. So, and for each bootstrap sample you would be calculating the variance, sample variances, and finally when I call this function it will return me the ratio of the sample variances, and that will be finally stored in bootstrap underscore st. Once this is done, now you can calculate your p value. So p value over here would be np.mean. So the absolute value of this, okay, so bootstrap st. So we'll compare the absolute values of this minus the absolute values of your observed st. Okay. So we have written this. Finally, we are going to check if p value that we have found here is less than equal to alpha. So then you are going to print reject H0, else what you will do? You will print fail to reject. Now we can print what is your observed ratio, observed ratio of the sample variances. So here we will write observe this one, right? If you want the p-value also, so we can give the command for that. So p-value would be what? P-value, here we have used this variable p-value. Sorry, I have not written this f over here, so it is not evaluating it and just directly printing it. Sorry for the mistake. So here the ratio comes out as 0.98. So the p-value that you have is 0.02, which is less than 0.05. So we are going to reject the null hypothesis that the two variances are same. Okay, so here you can see that I have used the ratio of the two variances, and that is why I have written in the bootstrap sample also I am considering their ratio only. So since there is no unique way of doing in bootstrapping, if you want, you can also consider the difference between these two, and here also you will consider the difference between the sample variances. So in that way also you can proceed. Sorry for that mistake. Please note that it should have been greater than equal to, right? We have to compare these two. It is not the difference between these two. Sorry. Okay, so we fail to reject in both the cases. So this is how you can do hypothesis testing in case of situations where you do not have any idea about the population from which the samples have been taken. That is basically a non-parametric case. Next, we will see how you find or how you test the claims that have been made about the population parameters in case it is coming from a distribution. You know the distribution, but it is not necessarily a normal distribution, because for normal distribution we have a very nice theory, exhaustive theory, whenever you have a normal population, how you can take the samples. But when you have different distribution, suppose it is Poisson or exponential, then how do you do the hypothesis testing in those situations? So that is equally important, and that is done by bootstrap concept. So we will see that next.